let's go ahead and get started on this stuff. Because we're a little bit behind my schedule, and how many of you guys actually completed pre-section quiz 4.4? Because we're actually doing that today. How many of you guys did not finish quiz 4.4? Okay, well, it's still open. I just reopened it a few seconds ago because defaulted back to the old date, but I reopened it again just in case you haven't. So, and 4.5 is what we're supposed to start today. We may start section 4.5, but I want to make sure you get this stuff down on section 4.4 and stuff. But I still got a few sections from section 4.3 to go over. So here's our section 4.3. And when we picked it up last time, we did this particular problem in all of its glory. And so I want to pick it up with this next problem. So we're still in section 4.3, but we're just doing the webwork problems from section 4.3. And I'll keep lubricating my voice, and maybe it'll sound a little bit better each time I do this. All right, here's the deal. Number 7 here, first part. Suppose that f double prime of x is continuous on the interval between negative infinity and infinity. If f prime of 5 equals 0 and f double prime of 5 is equal to 6, then f has a local what at x equals 5? Well, you got it. It's going to be either a maximum or minimum, 50-50 shot if you're guessing, but you shouldn't guess. There's only one shot at getting this problem right. So here's the deal. First derivative at 5 is equal to 0. That makes x equals 5 a critical number. You with me? Max-min number. But the second derivative, this is called the second derivative test, is equal to a positive 6. I don't care what the number is. The fact is the second derivative of 5 is positive. That means it's concave up. So if it's concave up and I've got a max-min point, what kind of point does it have to be? It's got to be at the bottom down here, which means it's got to be a minimum. Does that make sense? This is called the second derivative test. Similarly, f prime of 19 equals 0, and f double prime of 19 equals negative 6. Then f has a local what at x equals 19? It's got to be a maximum. And again, let's talk why. Since f prime of 19 equals 0, that means x equals 19 is a critical number. But f double prime of 19 is negative 6. I don't care what the number is. The fact that it's negative means it's concave down. Critical point, concave down, means the vertex or the max-min point has to be at the top, which means it's a maximum. Take a look at the next problem. The next problem, and then including the next section, is going to start bothering students. So you've got to listen very distinctly with what we're talking about here. There's easy problems and then there's harder problems. Now let me show you what we're talking about here. On this particular problem, on number 8, it says, it is given the graph of f of x. This is the easy guy. Determine whether the following conditions are true. So pretty much, it's true or false. Well, I know what you people do. You go through and hit true, 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 and then you try to figure which ones are wrong, and then go back and change those to false. And about 15 times later, eventually you'll got to get a right combination of answers to be able to get it correct here. Well, that's not the goal here. First times is the charm. However, let me tell you what's going to go on. This one's the easy one. They gave you the function of f of x, so you can really just read this stuff right off. In the next section, we're going to give you not the graph of f of x, but the graph of f prime of x, or f double prime of x, and start asking you questions about the original function. So those are the kind of problems you're going to have to outthink the question on. Okay? So, here we go. Given f of x, the graph of f of x, determine the following conditions are true or false. Is it true f prime of 3 is equal to 0? Well, there's 1, 2, 3, there's 3. There's the point. What is now? This is the function. This is y equals f of x. So this is exactly the way you expect to see it. What kind of derivative is right here at this particular function? It's equal to 0 because it has a horizontal tangent line. Does that make sense? So this is True. Look at part 2. True or false? F double prime of x is greater than 0 if 0 is less than x, which is less than 2. Now, let's understand the concept. F double prime of x means what? We're doing second derivative, which talks about what kind of concept here? Concavity. So the second derivative greater than 0 means the function is concave up. Is it concave up on the interval between 0 and 2? True or false? Well, look at the graph. It goes down and then keeps going down and eventually comes back up again. Is it completely concave up here? No. That's false. Second derivative measures concavity. First derivative measures increase, decrease. Second derivative measures concavity. This is the nice guy because you can read it right off the graph. Wait, I'll get to some more problems again today. Number 3. F double prime of x is greater than 0 if x is less than 0. F double prime of x is greater than 0. That means, once again, second derivative greater than 0 means am I concave up for x is less than 0. Well, here's 0. Less than 0, what kind of concavity does this graph have? Is that concave up or concave down? That's concave up. That's true. Number 4. F prime of x is less than or equal to 0 if x is less than 3. Now, f prime measures what? Increase and decrease. For f prime to be less than or equal to 0, that means I got to be decreasing or at least a horizontal tangent line. Does that make sense? For x is less than 3. Here's 3. Look at x is less than 3. What's the graph doing? It's decreasing. That means the derivative is negative, negative, negative. What's happening right there at 0? It's a horizontal tangent line, but then it goes to decreasing again until it gets to 3, horizontal, and then it starts to increase. So this is true. We're going to, as you read a graph from left to right, the graph is going down. It is decreasing. True or false? F the prime of 0 is equal to 0. Shake your head yes. True. Because we just talked about it. The derivative right there has a horizontal tangent line. Now, it's not a max-min point, but the derivative here is equal to 0. Does that make sense? Questions? But this was the nice one because it gave us the graph of f of x. Well, here's another web work problem before we move on to section 4.4. Find the cubic function f of x equals ax cubed plus cx squared plus d. It has a local maximum values of 8 at x equals negative 2 and local minimum value of 6 at x equals 0. Okay? In this web work problem, and this is a web work problem that everybody has to do, your mission here is to tell the computer what is A, what is C, and what is D equal to. That's what you're supposed to do. Now, let me understand what we got here. This weird function, here it is, f of x equals ax cubed plus cx squared plus d, has a local maximum, local max, of 8 at x equals negative 2. Now, I'm going to put that into context. What does it mean when you talk about the value? That's the y-coordinate. It occurs at the x-coordinate. So when we have a local maximum at the point negative 2, 8. Remember, the value is your y-coordinate. Does that make sense? Continuing on. And a local minimum value of 6 at x equals 0. So we have a local min of 6. That's your y-coordinate at 0. Now, there's more stuff going on here than that because now you're playing detective work. How do you calculate maxes and mins? How do we find these guys to begin with? What do you got to do? You take the first derivative, set it equal to 0, and solve. Which also tells me, because we're talking about maxes and mins, that f prime of negative 2 is equal to 0, and f prime of 0 has to be 0 because they're max min points. The derivative at these points, in this case 2 and 0, have to be 0. All right, so now it becomes a math game. Figure out A, B, C, and D. So the first thing I'm going to do is, since I have a point, this is X, this is Y. So I can tell you this. When I plug in X is -2, so F of -2, which will be A times -2 cubed plus C times -2 squared plus D, that's got to be equal to 8. Does that make sense? And that gives me an equation. What's -2 cubed? -8, don't hurt yourselves. -8A. What's -2 squared? 4 plus 4C plus D is equal to 8. I have an equation. You with me? I also know that F prime of -2 has to be equal to 0. So what is F prime of X? Now remember, A, C, and D are constants. What is the derivative of AX cubed? 3AX squared plus, what's the derivative of CX squared? 2CX. Remember, C is a constant, A is a constant. What's the derivative of D? D being a constant. 0, so it goes away. So now I'm going to plug in F prime of -2. So F prime of -2 would be 3 times A times -2 squared plus 2 times C times -2. That's equal to 0. Cleaning them up. -2 squared is 4. 4 times 3 is 12. So 12A. 2C times -2 is minus 4C equals 0. There is another equation. Does that make sense? And now I got to go to my other point. They gave me that I go through the point 0, 6. So F of 0, which will be A times 0 cubed plus C times 0 squared plus D, that's got to be equal to 6. We'll clean that guy up. Yeah, no problem here. 0 times anybody is 0. What does that tell me? I've already got one of my answers. D has got to be equal to 6. It's a game. And the last one, F prime of 0 has to be equal to 0. F prime of 0 would be 3A times 0 squared plus 2C times 0. That's got to be equal to 0, but honestly, I'm sorry, that doesn't help you out. Because 0 squared is 0, C times 0 is 0. Yeah, 0 equals 0. That's great, but that's not a real equation I can actually do anything with. Does that make sense? But don't worry, I got enough information to solve this thing. What is D equal to? And got that guy down. Now, if D equals 6, I can go and plug him into this equation. This would give me -8A plus 4C plus D, but D is 6, is equal to 8. I can clean that up and subtract 6 from both sides. I get -8A plus 4C is equal to 2. You with me? I also have this other equation. And you notice I'm working really hard at lining these guys up. 12A minus 4C is equal to 0. This is called a system of equations. Now honestly, we really jump on this stuff when we get to linear algebra, but this is the elementary stuff, so we expect you guys to have had a little bit of background in this stuff in your high school math classes. So I've got these two equations. I got 2 equations and 2 unknowns. I should be able to solve this thing. I can either do elimination method or substitution method. It's your choice. Personally, because all my variables line up, I'm going to do the elimination method. -8A plus 4C equals 2, and 12A minus 4C equals 0. I'm going to add these 2 equations together, because if I add them together, what happens to my C variable? It cancels out. So I get -8A plus 12A is 4A. 4 plus 4C minus 4C cancels, equals 2 plus 0, which is 2. Well, that's easy to solve for C now. Divide by 4 on both sides, and I get A to be equal to 1/2. So I can go up here and plug in A as 1/2. And now that I have A and C, I can go back to any one of these equations and solve for the C part. A and D, I can solve for C. So I'm going to use this second equation here. I got 12a minus 4c equals 0. I now know that a is equal to a half, so I can plug it in. 12 times a half minus 4c equals 0. Half of 12 is 6 minus 4c equals 0. I'm going to subtract 6 from both sides. I get negative 4c equals negative 6. Divide by negative 4. Reducing my fractions, negative divided by negative positive. 6 divided by 4 is 3/2. And so I end up getting my solutions of A in my problem. A is 1/2, C is 3/2, and D is 6. It's using the information about the original function, and because these are max-min points, the derivatives being equal to 0, creating systems of equations. Everybody's got a web work from section 4.3, just like this. Does that make sense? Questions? All right. Section 4.4. Now, I kind of stopped short last time. I was still doing section 4.4 because I actually had, what was it, on the video that you guys, pre-section video you guys watched, I actually did more stuff than was actually up here and stuff. Well, who cares? And more stuff is always good. But here's the deal on this thing here. Now, please watch the pre-section video because I took a sledgehammer and I beat this problem to death. Okay? But what we're going to do for you guys is going to be focusing on similar problems. You see, let me talk about this problem just in particular, but you've watched the pre-section video on it. This problem was f of x equals x squared divided by x squared minus 4. Okay? It has a problem. Do you know what problem this equation has? F of x equals x squared divided by x squared minus 4. It's a rational expression where the domain has some issues. The domain is not all real numbers. What's my domain problem here? Well, it's division, so I can't divide by 0. What makes me divide by 0? What values of x? 2 and negative 2. And they end up becoming vertical asymptotes. But here's the deal. When I ask you for intervals of increase and decrease, we draw number lines for the first derivative. But on that first derivative, I got to continue to omit 2 and negative 2. When I ask you for intervals of concavity, I'm going to draw a number line for the second derivative. But on that number line, I've got to omit, because they don't exist in the original function, they're not going to exist on the derivatives, negative 2 and 2, and I got to put little holes there. It's already going to subdivide your number line into certain sections, and then you put your critical numbers up there and your inflection numbers, and then do your test values the same thing. That's the only real difference, is you've got to omit the points that don't exist, not just on the original function, but on the first derivative number line and the second derivative number line, to be able to get your intervals of increase and decrease and intervals of concavity. That was the main thing I was focusing on this particular section. Does that make sense? All right. So, that being said, all right, let me just do a particular problem here. I'll do this one because let me explain something to you. This problem takes too long. Did you guys enjoy watching me do this problem on the video? Was it about 15, 20 minutes before I took this thing? I'm sorry, but on a test, I don't have 15, 20 minutes for you guys to do a problem. I try to do as many problems as you can so you can screw up as many of them as you possibly can and still pass the test. That's my goal. I try to put as many problems on the test as I can, and hopefully you won't screw up that many of them, but you guys seem to do it somehow, some way. But nevertheless, here's the deal. On a problem like this, we're going to shorten it up. So let me tell you what my directions would be. It's this problem right here. I would like to know what the intervals of increase and decrease are. That's one question. We're not going to make you graph it. I mean, we're not going to make you find intervals of increase and decrease, find the critical points, find the points of inflection, find the asymptotes, vertical and horizontal, find the x-intercepts and y-intercepts. By the time we do everything, the full 75-minute time limit you have for the test will be done. So I've got to kind of shorten this thing up. This is a rational expression, and I'm going to ask you one or two questions about it. What is the intervals of increase and decrease? Here's the deal. You've got to recognize this. F of x, there's your function, x squared over x squared minus 4. Okay? You got to notice there's a domain issue. What is my domain? My domain, notice I have a denominator. So x squared minus 4, the problem is going to occur if that's equal to 0. Solve it. Well, it factors nicely. Merry Christmas. So it's x plus 2 times x minus 2 equals 0. That means x equals negative 2 and x equals 2. These are what we call vertical asymptotes. These are holes in the graph. You can't cross these lines on the graph. Does that make sense? So you automatically have got to, when I talk about intervals of increase and decrease, when you draw your little number line, you're going to have to omit negative 2 and positive 2. And for intervals of increase and decrease, we're talking about a number line for the first derivative. If I ask for intervals of concavity, it's a number line for the second derivative. And you're still going to have to omit those two problems. Does that make sense? Now, how do I find critical points? I'm going to take derivative of this dude. Well, it's a pain in itself. What rule do you have to use to take derivative of x squared divided by x squared minus 4? Quotient rule. Drill the top times the bottom minus the top times drill the bottom all over the bottom squared. Drill the top. 2x times the bottom, x squared minus 4. Minus the top, x squared times drill the bottom, 2x. All over the bottom, x squared minus 4 squared. Clean him up. So f prime of x would be equal to, distributing here, 2x cubed minus 8, I can do math, 8x minus 2x cubed all over x squared minus 4 squared. Notice my 2x cubes cancel there. This gives me my derivative of negative 8x over x squared minus 4 squared. How do you find critical points? What are you going to do? Set it equal to 0 and solve. And when I have a fraction set equal to 0, first thing I'm going to do is multiply both sides by my common denominator here. And this will just cancel, leave me with negative 8x equals 0 times anybody is 0, divide by negative 8, and I get x equals 0. This is my CN. If I ask for the critical point, go and find the y coordinate for the guy. Does that make sense? This is my critical point. This is the number I'm also going to put on my number line. X equals 0. That was the only one. So now to find intervals of increase and decrease, there's my number line. Here's my derivative. Negative 8x over x squared minus 4 squared. And now we're going to do test values. Pick a number less than negative 2. Negative 3. And I'm going to plug him into my first derivative. And I got my handy dandy calculator right here ready. So let's do that. This would be negative 8 times negative 3 divided by parentheses, another parentheses, negative 3 squared minus 4 close parentheses squared. 0.96. I don't care what the number is. What's the sign of it? Positive. Pick a number between negative 2 and 0. I choose negative 1. Plugging negative 1 into this thing, I'm going to replace all my negative 3's with negative 1. Saves me tons of time. And I end up getting 0.888889. 0.8889. I don't care what the number is. It's positive. Now pick a number between my critical number right there at 0 and 2. You're right, I'm going to choose 1. When I plug in 1 into this thing, get rid of all the little negative ones and make them positive ones, I get negative 0.889. It's negative. Now pick a number bigger than 2. I choose positive 3. I plug it into my derivative. So call that thing, that derivative back down, and just insert 3's in place of those 1's. And then I'm getting a negative 0.96. It's negative. So, to answer the question, what are the intervals of increase? We traditionally write this in interval notation right off the number line. But remember, you've got to omit points that don't exist on that function. So the answer is it's increasing between negative infinity to negative 2 union negative 2 up to 0. You had to skip over the vertical asymptote at negative 2. Where is it decreasing at? Picking up it at 0, going to 2, union to to infinity. There's my answer. Does that make sense? And this is traditionally what we're going to ask you guys on test. We're not going to go out of our way to make you do the 14 steps of glory of trying to figure out a problem, starting at the function and talking about the first derivative. Well, first off, you got to talk about the domain, the range, the vertical asymptotes, the horizontal asymptotes, which is all chapter 1 stuff, the x-intercepts and y-intercepts from high school. Then you got to talk about intervals of increase and decrease and critical points. Then you got to talk about inflection points and intervals of concavity, and then put the whole darn thing together. It'll take you 25, 30 plus minutes to do any decent problem like that. And that's just way too long of a problem to do. So we're going to subdivide it. We'll give you a problem and ask you particular questions like, what are the intervals of increase and decrease? Or maybe what's the interval of concavity? You had to go after the second derivative, but you still had to identify the domain. Does that make sense? Now, turn page. More on section 4.4. All right. This is the ones, 4.4, is where they start to try to get you to be a little outthink the problem. This is a mental game at this point. All right. We know about a function. Max min points, inflection points, increasing, concave up, concave down. What's the deal? To find max min points, the derivative is equal to what? 0. Inflection points, how do you find those suckers? The second derivative is equal to 0. How do I find intervals of increase? I draw my number line, and basically it's increasing where the first derivative is positive. Decreasing, the first derivative is negative. What about concave up? Second derivative is positive. Concave down, second derivative is negative. But what the deal is this. We are not going to be giving you the original function. We're going to give you, like in this example, the derivative graph. Not the original graph, that's too easy. We're going to give you the derivative graph. And we're going to make you outthink the problem. Now, so when we're talking about the derivative graph, this is f prime of x. And they're going to ask you some questions. And it's the same kind of questions, true or false. But you got to think the derivative. So this is your derivative graph. So remember, a graph is positive when it's located above the x-axis. Our graph is negative when it's located below the x-axis. If I was interested in the second derivative information about the function, I would actually have to take the derivative of the first derivative, right? And the derivative of a graph is where you increase and where you decrease. So you've got to outthink the problem. So if I want to look at this graph right here and go, where is it concave up? That's where the second derivative is greater than 0. You with me? But this is the first derivative, so I got to take its derivative. The derivative of the derivative graph is where the derivative graph is increasing or decreasing at. So here it's going up, here it's going down, here it's going up. Does that make sense? So between negative infinity up to this point, which is 0, it's concave up. And at that point right there, this is where the function's increasing. See, increasing means derivative of the derivative, so we're talking about the second derivative. It's also concave up from 1 to infinity. You got to outthink the question. Okay? So we try to give you hints. And so if you're looking at the derivative graph, max min functions are the roots, the place that cross the x-axis. Because how do you find max mins? The first derivative equals 0. When you graph, the derivative graph equal to 0 means you cross the x-axis. Inflection points are the max min points of the first derivative. It's where the second derivative is equal to 0. So the derivative of the derivative. So it has a horizontal tangent line there. So they're max min points. Increasing is when the function is greater than 0. That means it's above the x-axis. Decreasing, the function is located below the x-axis. Concave up is what we just talked about, is where the first derivative is increasing. Concave down is where the first derivative is decreasing. Again, outthinking the problem. So, here we go. Web work problem. True, false. One shot. You either win or lose. Given the graph of f prime of x, state whether it's true or false. Is 1, f concave downward on the interval between negative infinity to 0. Negative infinity is here, all the way up through 0. Now, I know this thing looks like it's concave down, but no. And we're not talking about f prime. We're talking about f, the original function, right? So, is it concave down? Well, the fact of the matter is, this is your first derivative graph. If you're talking about concavity, you want information about the second derivative. So you want the derivative of this guy. The derivative of a graph is where it increases and decreases. What's this function doing as you read it from left to right? It's increasing. That really means it's concave up. This is false. Gotta outthink the problem. This is what makes it tough. Catch a pattern. F has a local maximum at x equals 0. Now at x equals 0, you're right. X equals 0 does have, it's an x-intercept here across the x-axis. But to be a maximum, okay, this is the original function. To be a maximum, the first derivative had to be increasing. You hit the maximum, and then the first derivative has to decrease. You got to go up and then go down again. Does that make sense? At 0, what is the derivative just before 0? Remember, this is the derivative graph. What's the derivative of values just before 0? They are negative because they're located below the x-axis. What are the derivatives after you go through 0? Where's the graph located at? Below the x-axis. They're still negative. You never change going from increasing to decreasing or decreasing to increasing. Does that make sense? You went down, hit 0, and went down some more. That doesn't make maximums or minimums, actually. This is false. Because this, at 0, it is an inflection. I mean, it's a 0. It's an x-intercept, which means the derivative does equal 0 there, but is it a maximum point? Well, just before it, the derivative was negative, so you went down. You hit 0, and then the derivative's down again. So you go down, hit 0, and then go down some more. That's not a max-min point at all. So another false. Number 3, is f decreasing on the interval between negative infinity to 1.5? 1.5 is right here. Does that make sense? To be able to decrease, the derivative has to be negative. Does that make sense? Now, the answer for this problem is derivative negative? Well, look over here at negative infinity. Remember, this is a derivative graph. It is located below the x-axis. What kind of values does that make it? Negative. It's negative. It's 0 right there, but then it's negative again until it's 0 right there. Does that make sense? So it's never positive is the point. Does that make sense? To be decreasing, they really state the derivative had to be less than or equal to 0. This is actually true. Okay, fine, you hit the 0 point only for a moment, but you never went a positive slope is what we're trying to say here. Does f have an inflection point at x equals 0? And what's an inflection point? The second derivative had to be equal to 0. So the derivative of the derivative has to be equal to 0, right? So when you're looking for the derivative equals 0, you're looking for max-min points of the derivative. Is 0 a max-min point? Look at the graph. It's a maximum little point there. Does that make sense? The derivative of that point right there is 0 because that's a horizontal tangent line, but it's the derivative of the derivative graph, which means the second derivative equals 0. This is true. As we stated up here, to be inflection points, f prime of x, to be inflection points, f prime of x has to be a max min. That is actually a maximum point. Over here is a minimum point. So at 1 is where the other inflection point is going to be at. Number 5, is f decreasing on the interval between 0 and 1? Yes, true or false? I'll just let you throw that one at you. Yes or no? True or false? Between 0 and 1, is f decreasing? The original function is decreasing. Remember, this is the graph of the derivative. So between 0 and 1, is it located below the x-axis? That means the derivative is negative. And derivative is negative means it's decreased. Yeah, that's true. And then the last one. Is f increasing on the interval between 1.5 and infinity? Is f increasing? But make sure you get the right answer and the right reason for the answer. It's not because, hey, the slope is positive. It's not that at all. The fact is, at 1.5 over, remember this is the derivative graph, and it is located above the x-axis, which means the derivatives are positive. And derivatives being positive means it's increasing. So it's true, but because it's located above the x-axis. That's why. Does that make sense? Again, this stuff makes it tough because you got to outthink the questions and stuff. So we got some more problems here. Same idea. For each of the following is the graph of the derivative. There's two of them here. There's this one and there's this one. State where the original function f of x is increasing, decreasing, has maximums and minimums, concave up, concave down, inflection points, and then sketch the actual graph. Well, that sounds like a lot of stuff to do. So let's see if we can just sketch the original graph, and then we can talk about where it's increasing and decreasing and stuff like that. All right, so remember, look at part A. This is f prime of x graph. We're supposed to actually graph the original function. So I'm going to slide it up like this, okay? So here we go. If you're looking at a derivative graph and you want to actually graph the original function, the first thing you need to find is your max-min points. Where are the max-min points? This is where I'm going to start this thing out. It is a strategy here. Where's your max-min points at? Remember, max-min points are where the derivative is equal to 0. Here's the derivative graph. Where is it equal to 0 at? At -4. -4 there. What is that? 2. And with this one right here, what is that? 2, 3, 4. I guess that's a 5 right there. 5. So at -5, 2, and 5. These are your max-min points. That's where I'm going to start. I know I've got max-min points. Now, what kind of max-min points are they? Look at -4. Right here at -4. Is it a maximum or minimum? Look, just before -4, the derivative is negative. Right? Remember, this is the derivative graph. And that's after the derivative is positive. So if the derivative is negative, what does that mean it does? The original function goes down. When the derivative is positive, it goes up. What kind of point does that make it? This one's going to be a minimum. So at -4, you're going to have a minimum point. I don't know what the coordinate is, so I'm just going to put a dot down there, and I'm going to label him as minimum. I know that's how low it goes. Being a minimum is going to be at the bottom of the graph. That's basically it. So this is a general shape graph. This is not particular because they didn't actually give me coordinates and values to plug into this thing. So I'm getting a general shape of the graph. Look at 2. What kind of max-min point is it 2? Well, just before you get to 2, the derivative is above the x-axis, means it's positive. Derivative means it's increasing. And then just after 2, it is decreasing. You with me? So if you go up and go back down, that makes a maximum. So at 2, it's a maximum. So somewhere, pick your favorite y coordinate. I'm going to declare it to be 3. And that 2, this is a maximum. But there's one more critical point on this thing. What is it? It's 5. Just before 5, the derivative was negative. That meant I went down. And then after it, the derivative is positive. It goes up. To go down and go back up, 5 is going to be a minimum. I'm going to declare it to be, I don't know, right there is good enough. And we'll declare it to be minimum. So, in terms of answering all their questions, I can let you know this. X equals -4, it's maximum point. X equals, excuse me, I screwed that up. X is a minimum point. X equals 2 is a maximum point, and X equals 5 is a minimum point. Just denoting things I just discovered. After you find max-min points, then you want to find your inflection points. You notice I'm going after the big points, max-min, critical points, and inflection points. But an inflection point is where the second derivative is equal to 0. But when you look at the original, when you look at the derivative graph, it's the max-min points of the derivative graph. Where are my max-min points? I got 2 of them. Where are they? At -1 and at, what is that? 2, 3, 3.5. Right? -1 and 3.5. So -1, I'm going to label a point. I'm going to put him anywhere I want to, right here. I'm going to label him as an IP. He is an inflection point. The other one is at 3.5. And usually your inflection points are somewhere in the middle between your maximums and your minimums. So here's a max, here's a min at 3.5. I'm going to put it at 1 right here at some coordinate. I'm just picking them out. It's another IP. So I've got IP's inflection points at x equals -1 and at x equals 3.5. Now, we're going to put the picture together, and then I'll go answer the rest of the questions. All right. Look below -5. The derivative is negative. That means I'm going down. But what about the concavity? What slope does this guy have? This one is a positive slope. Does that make sense? But remember, this is the derivative graph. So the derivative of the derivative means the second derivative. The second derivative is positive. So that tells me I'm decreasing and I'm concave up. That's what it's going to look like. I'm decreasing, but I'm concave up. Does that make sense? Once you hit -4, going between -4 and 1, the derivative is above the x-axis. That means I'm increasing. The slope is positive, which means it is concave up. So increasing concave up looks like that. Remember, I got to hit all my little points that I just made. Now, once I hit 1, now the derivative is still positive until I hit 2 over here, because it's above the x-axis. But what about the derivative of that guy, which makes it the second derivative? It's sloping down, which means it's concave down. So now I've got to be concave down, but I still got to increase. Increasing concave down. Once I hit 2, now my derivative is negative. It means I'm going down, but my concavity, the slope is negative. It's got to be concave down. So it's decreasing and concave down. Looks like that. And once I hit 3.5 here, after that, I've got to, I'm decreasing, but now my slope is positive, which means I'm concave up. And once I hit 5, now I am positive. My derivative is positive. I'm increasing. My second derivative has a slope is positive, so my second derivative is positive, so I'm increasing and concave up. That's what my picture will look like. Now let's go back and answer their questions. They want to know intervals of increase, intervals of decrease, concave up, and concave down. All right, let's see if they answer the question now, and I'll blow this up. Because once I've got that, now I've got the original picture, I can just use it normally. I'm increasing between what? -4 to 2, union, where else am I increasing? From 5 to infinity. That's where the graph is going up. Where's the graph going down at? From -infinity to -4, union, decreasing 2 to 5. Where is it concave up at? Concave up from -infinity to -1, union, or concave up from 3.5 to infinity. Where is it concave down at? Concave down between -1 and 3.5. Now I've answered all their questions. Does that make sense? It takes practice to do this. So we got part B over here to do. Let's take a look at this guy. Where do I start is the hardest part about these kind of problems. They've given me the graph of the old derivative there, and they want me to figure out what the original function looked like. First thing you start with is your max-min points. And remember, on the derivative graph, the max-min points are your x-intercepts. So where are my max-min points? Well, there's the origin there. There's -1, -2. What is that? -3.5. And at 1, 2, 3, and positive 3.5. Looks like at -3.5 and positive 3.5 is where I have my max-min points. So what kind of max-min point is this guy? Well, just look at -3.5. Just before it, the derivative is negative. That means I'm going down. Just after it, the graph is above the x-axis, means derivative is positive. To go down and then go back up, that makes this dude a minimum point. So at negative 3.5, so 0, 1, 2, I'm sorry, negative 2.5, I can count hash marks, 0, 1, 2, 3, it's negative 2.5. So at negative 2.5, it's a minimum point, so I'm going to go down here somewhere and declare it to be a min. Just put a dot there. This one is 1, 2, 3. This one is 3.5. But just before 3.5, the derivative is positive. That means I was going up. And after 3.5, the derivative is negative. It's going down. That makes it a maximum. So at 3.5, it's a maximum. I don't know, just put a point somewhere above just to kind of emphasize it's big. Because they didn't tell me what the y coordinates are, so I'm guesstimating on those guys. Okay? After I find my max min points and decide their style, maximums or minimums, then I'm going to go after the inflection points. Inflection points, by definition, where the second derivative equals 0, but when you look at the first derivative graph, it's your max min points. There's only one of them. And that point is at what? 1. So over here at 1, we have an inflection point. And somewhere between these two guys, it doesn't matter where, but it's got to be in the middle between them, this is going to be your IP. Now, start to graph this guy. Look below negative 2.5. The derivative is negative. That means I'm going down. However, the slope of the first derivative is positive, which means it is concave up because it's a positive slope. So I got to be going down and concave up. It's going to look like this. Does that make sense? Now, once I pass 2.5, the derivative is positive because it's located above the x-axis, and my slope is positive, which means I'm still concave up. So I've got an increase in concave up until I get to the next point. But once I hit 1 right here, now my derivative is positive, so I'm still increasing, but my slope is negative. It means I'm concave down. And once I hit 3.5, my derivative is negative because it's located below the x-axis, and my slope is negative. I've got to be decreasing in concave down. And there's the general shape of the graph. And then I can go back and answer the questions. At x equals negative 2.5 and x equals 3.5, these are your max min points, and at 2.5 is a minimum, 3.5 is a maximum. At x equals 1 is your inflection point. It is increasing on the interval between, is that negative 2.5 to 3.5. It is decreasing on the interval between negative infinity to negative 2.5, and again from 3.5 to infinity. It is concave up to the inflection point there from negative infinity to 1, and it is concave down on the interval between 1 and infinity. And I've answered all my questions. But notice I got the picture first, and then I went back and answered all the questions. Saves lots of time. Does that make sense? It's not hard, but you got to catch the pattern on it. So it takes practice. Section 4.5. Told you I'd get there today. All right. Section 4.5 is one of these very large sections. By the way, when is section 4.5 pre-section quiz stuff due on section 4.5? Yeah, I knew I was going to get there, so hold on. Scroll down. Section 4.5. When is the pre-section quiz due? Today. So how many of you guys have done section 4.5? Proud of you. How many of you guys haven't done 4.5? Shame. But you got until 11:30 tonight, so make sure you get it done, all right? Now, section 4.5 is a large section. And what I mean by large section, I mean big point totals. This is I told you guys about There are two major word problems that are going to hit you hard on the old final exam. Related rates, chapter 2.7, and optimization, section 4.5. Optimization. It's a word problem where we want to maximize something or other or minimize something or other. You know, to maximize or minimize anything, you've been programmed. You're going to take derivative, set it equals 0, and solve. This is what you do. It is your life. Get used to it. This is what you do in Calculus 1. To maximize or minimize, including Calculus 3, you'll see this stuff again, you take the derivative, set it equal to 0, and solve. This is where your max min points show up at. So, in this particular section, I try to create basically steps to get you guys to do, and just about 90% of word problems that are max min problems will follow these 5 steps to glory. So I'm trying to help you out in what to do. Okay? But some problems are easier than other problems, and you don't actually have to do all the 5 steps. But the 5 steps is kind of a guideline to get you guys to do all these word problems. So, step 1. What are you going to do? Read problem, draw a picture, label, and come up with something called the objective equation. So, let me go over here, and again, I wrote these things down from the textbook, but let me go over here. Now, I did this problem on the pre-section video. I did this problem on the pre-section video. I did this problem on the pre-section video. So let's start with number 4. All right. Now, this one, I drew the picture for you because everybody's got one on WebWork just like it. The U.S. Postal Service will accept a box for domestic shipping only if the sum of the length and the girth, which is the distance around, does not exceed 108 inches. Find the dimensions of the largest volume box with a square end that can be sent. So we are trying to basically send the biggest package possible for our money, right? So, what did they say about this particular box? Now, quote, step 1, read problem, draw a picture, label. I drew your picture because I did say this thing was going to have a square base. So as a square base, I'm going to call this guy x by x. Notice, I'm putting the variables in it. And we're going to have a length. I don't know what the length is. That'll be a different variable. I'm going to call it y. Yes, you're going to have multiple variables with this mess. Okay? So it's a square base, x by y. All right, now, the U.S. Post Office will accept a box for domestic shipping only if its sum of its length and the girth does not exceed 108 inches. Find the dimensions of the largest volume box. Step 1, draw a picture, label it, and come up with the objective equation. Now I'm using these fancy words called the objective equation. You are in calculus. You know what your objective is? To make an A. How do you make an A when it comes to maximizing and minimizing? You take the derivative of somebody, set him equal to 0, and solve. What are you trying to maximize or minimize? Volume. So I want a volume equation. What is the volume of a box? That requires your knowledge. If you don't know it, go back to the 3rd grade and figure it out. What is the volume of a box? Length times width times height, based upon my letters. Because we did say this had a square base, right? So what is that? X times x by y, or better yet, volume equals x squared y. There is my objective equation. I have to read problem, draw a picture, label it with my own letters, and then come up with what I'm trying to, basically, the dude I'm trying to take derivative of. I want to maximize volume. So please understand this. You see that equation right there? X squared times y. I want to take derivative of this dude, set him equal to 0, and solve. That is my life. That's what I got to do. Take derivative, set equal to 0, and solve. But I got a problem. You know what my problem is? Too many variables. This is going to happen to you. So the second step is to come up with what we call the constraint equation. Now that's the fancy term from Dr. Stewart in our textbook, but the constraint equation is an equation with the given information. What was given in this problem? Quote unquote given. what was given? Some kind of numbers were given at you. Okay, because if they didn't give you this, the answer is infinity by infinity by infinity. Ship that one through the U.S. Postal Service system and see how that goes. So, we got something given. Only if the sum of the length plus the girth has to not exceed 108 inches. I told you there were some numbers given here. So the length plus the girth has to be equal to 108 inches. Now what's the length of this box based upon my variables? It was y. Plus what is the girth? The girth by definition is the distance around the box. What is the distance around this box? Remember, this was variable x, this is variable x, this is variable x, x because it's square. What's the distance around the box? 4x is equal to 108. Does that make sense? The distance around the box, also known as perimeter, but they call it girth. 4x. Does that make sense? Because it was square base. Now, what is the job of the constraint equation? What are you going to do? You're going to take the constraint equation and solve for one of the variables and plug it into the objective equation. So this was step 1, this is step 2, this is step 3. Solve for one of the variables. I'm going to solve for y because it's so much easier. What's y equal to? 108 minus 4x. And I'm going to plug into the objective equation. So this is going to give me volume is equal to x squared times y, which is 108 minus 4x. And I'm going to clean it up. Volume equals 108x squared minus 4x cubed. Here comes step number 4, and put a big old star by step number 4. Step number 1, just to remind you, was read the problem, draw a picture, label it, and come up with the objective equation. The equation you want to take derivative of. The equation you can maximize or minimize. Step 2, come up with the constraint equation, which is the equation for the given information. Step 3, solve for one of the variables on the constraint equation and plug it into the objective equation. Step number 4, this is your calculus. Take derivative, set it equal to 0 and solve. Okay? Derivative equal to 0, solve. This is what your life is all about, being a Calculus 1 student. So V prime is equal to, what's the derivative of 108x squared? 216x minus what's the derivative of 4x cubed? 12x squared. Set it equal to 0 and solve. Well, what can you factor out of this thing? I can clearly pull out an x. Can I pull out a 12? Yes, I can. When I do, I can factor out a 12x. I'm left with, let's see here, 216 divided by 12 is 18 minus x equals 0. I'm going to set each factor with an x in it equal to 0 and solve. And I get x equals 0 and x equals 18. I get two answers, 0 and 18. You know what happens when you traditionally do a max-min problem and get two answers? Because we didn't specify maximum or minimum, one of them is going to maximize and the other one's going to minimize. One of them typically makes sense, the other one makes absolutely no sense whatsoever. Guess which one of my two answers doesn't make any sense? 0. Basically, remember this is x. I can have all length and no girth, and I can ship that. What is that, a rod going through the post office or something like that? So I'm not going to mail that. So x equals 0 would obviously minimize the volume. I would actually have no volume if I had all length and no width, if you will. Does that make sense? So what's the answer? 18. And then there is step number 5. Step number 5, and a lot of people ask me, well, Dr. Taylor, how can I improve my grade in terms of Calculus 2? I'm about to show you right here. Because step number 5 is where people screw it up at. You've done everything that you're supposed to. You took derivative, set it equals 0, and you solve. Here's where the payoff is. Here's the money points. Go back and answer the question. That's what people forget to do. Yeah, x equals 18. What does that actually mean? This is a word problem. It means nothing until you put it into the context of the problem. So, find the dimensions of the largest possible box. What's the dimensions of my box based upon the letters I created? The box is what? It's x by y. That's what they wanted me to find. And don't forget your units. It's a word problem. What is x equal to? We just discovered that. It's 18. 18 what? What is x measured in with this mess? Inches by 18 inches by y. I got to go figure out what y is. That's the job of the constraint equation. The constraint equation is your linking variable equation. Does that make sense? So as y is equal to 108 minus 4x, y equals 108 minus 4 times 18, and I'll stick that on the old calculator. 108 minus 4 times 18 is 36. So what is y equal to? 36 inches. So if you want to know the truth of the matter, go to the post office. If you wanted to know what the on domestic packages here, this is not that extra stuff you have to pay for on a standard domestic package. The biggest box you can send and they'll accept it is an 18 inch by 18 inch by 36 inch box. Mathematically, that's what it is. Yeah.
So we can leave it as x, and y if we label like a picture?
Yeah.
Not right, like length or...
Well, okay, all right. Yes, I'm happy with that because it's here. On web work, they're going to ask you what length is and what width is, and they're going to ask you to do this. To identify them, they would say that the, quote, width is less than the length. So, because in web work, they got to be very poignant in which numbers you're going to plug in. So which one's your smaller numbers? 18. So 18 would have been the width, and the length would have been the 36. And that's what you type in, because they would have told you, not just typing in the answers, which is 18 and 36, you got to put them in the red special blanks, and they're going to tell you which one's smaller than the other. So put the smaller one first, and the bigger number next, that type thing. But yes, absolutely we'll accept this. 100% accept this. Does that make sense? Okay? All right. Here's another one. Okay. Now this is one of those problems I warned you guys that, quote, some of the problems are easier than others. I can go through my 5 steps and I'll model it after that, but I don't need all 5 steps on this one because of the way the problem is built. Here we go. A box is to be made out of an 18, let's say inch by 10 inch by 18 inch piece of cardboard. Squares of equal sizes are to be cut out of each corner, and then the ends are to be folded up to form a box with an open top. Find the length, the width, and the height of the resulting box that maximizes the volume. And here comes web work. Assume that width is less than or equal to length. All right. So let me understand what this problem is. Now I'm going to draw pictures on this thing, but I'm also got a little manipulative here. So here we go. This is my little piece of paper. It is 10 inches by 18-inch piece of paper. They gave that to me, or a piece of cardboard. Okay? What we're supposed to do is we're going to cut out little squares of equal size out of each corner. So over here, assume, I know it's 11 by 8.5 by 11, don't care. Assume it's 10 by 18. I'm going to cut out little squares out of each corner. And they're squares, right? So how much am I going to cut out? I don't know. That's going to be the big question. So I'm going to call this guy X. X is the amount I'm going to remove. So I'm going to remove, by hand, little squares out of each corner. Does that make sense? So X by X, and they're all the same size. So this is X by X, X by X, and I am actually producing the variable that I'm plugging on this guy. Now, okay, I'm going quickly here because I see the time on the clock there, but that's all right. So assuming they're squares, okay, there they are, squares out of each corner, and this is what we got with these parts removed. You with me? Now, this is what we're doing. we're going to fold this thing up. So this is why I want to use my little manipulative. So, now when I was in school, back in the good old days, each student, when you were in the 7th grade, you had to take art appreciation, you had to take music appreciation, students had to take home ec, including the guy students had to take home ec, and you had to take shop. Girls had to take shop class. It was great. So this is something we did in shop class. Now I know you guys probably haven't seen anything like this before, but we would have metal tins, what we did, and we would take tin snips and cut out the corners out of this thing and fold it up, and it makes an open box top. In the old days, we would call this an ashtray. I know you guys haven't heard of that, but it's an ashtray that we would give to our parents, and they would be so proud of what Johnny made in class and show them to all their friends at bridge parties and stuff. So there it is. We're making ashtrays out of this thing. So when we flip this thing up, now you got to look at it from the mathematics perspective here. It is an open top box. What would the dimensions be? Because remember, on each corner, I removed an X. So when you flip it up, how tall is the box? You got to think about this stuff. How tall is it? It's X tall. What is the width of this thing? All right, so here we go. This thing, how long is this guy? It was 10 inches, but we removed an X on one side and we removed an X on the other. So when we did that and flipped it up, how long is this thing? Very good. It is 10 minus 2x. Does that make sense? How long is this guy? Well, this was 18 inches, but again, we took away an X on this side, an X on that side, and flipped it up. And so when I did that, it made it how much? 18 minus 2x. See, all this is part of that constraint. Does that make sense? Because what is the object of our game here? What do they want us to do on this particular project? What are we supposed to do? No. Maximize what? Volume. Object is to maximize volume. What is the volume of a box? It is length times width times height. The height, due to the constraints, see, the constraints were built in, so I'm not actually doing all those steps because you had to build this thing. The height is X. They say the width is less than the length. You with me? This is web work. So which one's the width? Which one's the length? Very good. The 10 minus 2x will be the width. That's smaller than the length, which is the 18 minus 2x. Does that make sense? Did I lose you guys anywhere? So your job is to make an ashtray for your parents that can hold as much ashes as humanly possible. Maximize the volume. All right, so here we go. So now put the constraints into your objective equation. Volume is equal to 18 minus 2x, the length, the width, which is 10 minus 2x, times the height with its x, and I'll just put it out front. So there it is. There's my equation. There is the height, this one is the length, and this is the width. We want to take the root of this guy, set him equal to 0, and solve. But now, you can do algebra. I can do the triple product rule, but no one remembers the triple product rule. Derive the first times the other two guys, times derive the middle times the other two guys, times derive the last guy times the other two guys. Too much work. So what I'm going to do is I'm going to clean it up first. I'm going to FOIL this mess out. Okay? So it'll be 18 times 10, which is 180. 18 times 2x is minus 36x. Minus 2x times 10, which is another minus 20x. And a minus 2x times a minus 2x is a plus 4x squared. So volume is equal to x times 180 minus 56x plus 4x squared. Now I'm going to distribute the x and get 4x cubed minus 56x squared plus 180x. I just wrote them in decreasing order just because it looked better. Does that make sense? I fold them out and distribute the x. Now, this is what we're all about. How do you maximize and minimize anything? What are you going to do? You're going to first take derivative, then set equals 0 and solve. And you got to think about the problem because you can get multiple answers, usually max, min, or whatever, and we're trying to maximize. So keep that in the back of your mind. Outthink the problem. What's derivative of 12x cubed? I screwed it up. What's derivative of 4x cubed? Even better, 12x squared. Minus what's derivative of 56x? 100 and what? 112x plus root of 180 is, 180x is 180. Set it equals 0 and solve. Here's your problem. This one I created off of web work. None of these guys are going to factor nicely. This thing sucks in terms of factoring, which means it actually doesn't factor, which means it's a quadratic that's set equal to 0 that you can't factor, which means what? Quadratic formula. X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So x would be equal to negative 112 plus or minus the square root of b, which is a negative 112 squared, minus 4 times a, which is 12 times c, which is 180, all over 2 times 12. I got a question for you. How many answers you can get on this quadratic formula? 2, that plus or minus. Now I'm going to put it on my calculator here. And double check me on this, but let's see if I get this. I get 2 answers. I get x equals 7.270083225, and I get x is equal to 2.0632510108. There are 2 answers you get from the quadratic formula. What did x represent? Go back and think about the problem. This is that part 5. Answer the question. What did x represent? X represented the amount that I removed. I got 2 options, 7.27 inches or 2.06 inches. Now the darn thing's only 10 inches wide. And if I take an x 7.27 inches on one side and 7.27 inches on the other side, I've done Star Trek stuff because I've imploded and actually taken away more than I actually started with. Does that make sense? So which means this, mathematically, it actually minimizes something with the quadratic form or the cubic form, but that's not your answer. So the answer is x is equal to 2.0632510108. Okay? But remember, now web work, that would be the height. You got to tell them what the width is, and you got to tell them the length. Remember, the width was 10 minus 2x, and the length was 18 minus 2x. And this, don't forget, it's in inches here. So here we go. So it'll be 10 minus 2 times x, which is 2.06. 3250108. I end up getting 5.87349978 inches. And then I've got to do what? You take it and make it 18 minus 2x, and I'm just changing 10 to 18, and it is 13.87. It's web work, give them all the decimals. 349978 inches. In other words, my ashtray that I built for my parents was 2 inches long, 2 inches high, 5.87 inches long, and 13.87 inches long, and that would hold the maximum amount of ashes that my parents' friends who smoked cigarettes in the old days could come over to the house and play bridge and stuff. Does that make sense? Study this because they're great problems, but remember step 5. Don't forget to go back and answer your questions. I'll see you guys. Don't forget review on Friday and class on Tuesday. We'll finish up a lot more problems.